On March 26, 2024, just a few weeks ago if you're watching this as it comes out, a large container ship struck one of the main support piers of the Francis Scott Key Bridge in Baltimore, Maryland, collapsing the bridge, killing 6 construction workers, injuring 1 more, and seriously disrupting both road and marine traffic in the area. There's a good chance you saw this in the news, and hopefully you've seen some of the excellent content already released by independent creators providing additional context. I got a lot of requests to talk about the event, and I usually prefer to wait to discuss events like this until there are more details available from investigations, but I think it might be helpful to provide some context from an engineering perspective about how we consider vessel collisions in the design of bridges like this one, and why the Francis Scott Key Bridge may have collapsed. I'm Grady, and this is Practical Engineering. Today we're talking about vessel collision design for bridges. The Francis Scott Key Bridge was a steel, arch-shaped, continuous through-truss bridge. I'm working on a video that goes into a lot more detail about the different kinds of bridges and how they're classified, but this bridge had kind of a structural medley of styles, so let me hand it off to our special guest correspondent, Road Guy Rob, to break that terminology down.
Well, Grady, I'm in Long Beach, California today, standing on top of this brand new bridge that replaced an old arch truss bridge that used to be right there. It kind of looked like a baby key bridge, and the Port of Long Beach is happy that it's gone.
The Gerald Desmond Bridge was a truss bridge. Instead of having one big, large beam, a truss has lots of smaller, connected structural members all attached together. This creates a rigid structure that's much lighter weight than a big, heavy beam.
And that makes trusses efficient and clever when they work. Both the Key Bridge and the old bridge that used to be here were through truss bridges.
It's a sort of arch shape, and the driving deck is suspended below the truss, so you sort of drive through the arch.
But it's not an actual arch with like a keystone and all the pieces pushing horizontally to hold each other together. No, this through truss bridge has no hinges or joints at the main supports, nothing that breaks it up into sections.
So that's why engineers called the Key Bridge a continuous truss bridge.
It's all one big piece, and it's all bolted and welded into a single rigid truss across its entire length, and then that load distributes across all 3 spans of the bridge. Now, the approach roads on each side are entirely separate bridges, even though they link together.
They just look like concrete roads sitting on top of simple girder spans.
Well, you ask, what happened to that baby Key Bridge in Long Beach? Well, the only way you're going to see it now is to turn on Grand Theft Auto 5 and look at the fictionalized version of it, immortalized in Los Santos for all time, because when this bridge opened, the Port of Long Beach demolished the old bridge, and the last scraps of it got hauled away back in October.
In its place, this new, fancier-looking cable-stayed bridge, the Long Beach International Gateway.
And what the Port of Long Beach did in studying to build this bridge and the list of improvements they came up with might give us some clues what Baltimore might want to end up doing when they replace the Key Bridge down the line. And we'll talk about that in just a moment.
When the Dali container ship lost power and drifted into the southwest pier, the support collapsed and most of the truss and deck fell with it. Both the southwest and central spans fell roughly vertically with the loss of support from the damaged pier. Part of the truss on the northwest side separated from the unsupported section and rotated toward the northeast span, taking several of the approach spans with it. Thankfully, the ship had put out a mayday call before the impact, allowing police officers at either end of the bridge to close it to traffic. Tragically, it wasn't enough time to get the crew of 8 construction workers off the structure before it fell, 6 of whom lost their lives. Just dealing with the salvage and removal of the steel and concrete debris left over from the collapse has been a massive undertaking. Within a week, engineering teams were on site, measuring, cutting, lifting, and floating away huge chunks of the wreckage in separate salvage operations for the main bridge, approaches, and the vessel. As of this writing, they're still working hard on it. At least 7 floating cranes were involved, including the famous Weeks 533 that pulled U.S. Airways Flight 1549 from the Hudson River in 2009. This was essentially a massive Jenga tower. The order of operations and the precision of each cut and each lift mattered. With so much debris underwater, they had to map it out to understand how everything was stacked together. Access was a major challenge, and the stresses in the wreckage were hard to characterize, so it's been a slow and deliberate process requiring careful planning and tons of skill to do safely. Fortunately for Baltimore, there are large industrial facilities in the port that can process the thousands of tons of material that will ultimately be removed. Of course, reopening the port to shipping traffic is a huge priority. A small channel was marked out under one of the approach bridges for smaller vessels like tug and barge traffic, and the Army Corps of Engineers is making good progress on opening up the main channel. But it isn't clear when full-scale operations of the port will be able to resume. Shipping traffic isn't the only traffic affected either. The bridge carried thousands of road vehicles per day that now have to be rerouted. There's a tunnel under the harbor that provides a decent alternate route, but trucks with hazardous materials aren't allowed through, requiring an enormous detour around the city. It's been more than a month since the event, but it will likely be a year or more before we get an official report documenting the probable cause of the failure. In the US, events like this are investigated by the National Transportation Safety Board, or NTSB. This independent government agency is extremely diligent, and often diligent also means slow. But events like this are how the field of engineering evolves. Human imagination isn't limited to past experience, but in many senses, engineering is. We just don't have the resources to answer the millions of what-ifs that might coalesce into a tragedy, so we lean on the hard lessons learned from past failures. When something terrible happens, it's really important that we collectively get to the bottom of why, and then make whatever changes are appropriate to our engineering systems to prevent it from happening again. But at the risk of stating the obvious, the failure mode in this case is pretty clear. You probably don't need an engineer to explain why a massive ship slamming into a bridge pier would cause that bridge to collapse. I think what's less obvious is how engineers characterize situations like this so that bridges can be designed to withstand them. Collisions with bridges by barges and ships are not a modern problem. Technically, they're called elisions since a bridge isn't moving, but that term is used more in the maritime industry than by bridge engineers. Between 1960 and 2014, there were 35 major bridge collapses resulting from vessel impacts, and 18 of those were in the US. We just have such a big network of inland waterways, and that means we have a lot of bridges. 2 spans of the Queen Isabella Causeway Bridge in Texas collapsed in 2001 when barges collided with one of the piers. A year later, a bridge carrying I-40 over the Arkansas River in Oklahoma was hit by barges when the captain lost control, collapsing a major portion of the structure. In 2009, Pops Ferry Bridge in Mississippi collapsed after being struck by a group of barges. In 2012, the Egner's Ferry Bridge in Kentucky fell when a cargo ship tried to go through the wrong channel. Before any of those, though, the Sunshine Skyway Bridge in Florida put a major focus on the problem. In 1980, a bulk carrier ship lost control because of a storm, crashing into one of the piers and collapsing the entire main span of the southbound bridge, killing 35. The event brought a lot of new awareness and concern about the safety of bridges over navigable waterways. But piers aren't the only parts of a bridge at risk from ships. I'll let Rob explain.
The Key Bridge got into trouble because of a horizontal elision. That's where a ship moves side to side in the wrong way and hits something it's not supposed to. Here in Long Beach, that really wasn't their concern primarily because the old bridge columns were way inland here. So there was no way for a ship to exit the waterway and hit the column because the column was in lots of dirt. And the new replacement bridge takes no chances at all. Look how much farther onshore those columns are now. No, the Port of Long Beach were far more worried of the old Gerald Desmond Bridge getting hit vertically. The old bridge was 155 feet tall. That's like a 15-story building. And if that sounds pretty tall to you, it sounded pretty tall to them back in 1968 when they built the bridge. But as we now know, ships are getting bigger and fatter and taller, and 155 feet wasn't cutting it for some of the modern ships that were trying to get into the back part of the port where there's a lot of cranes and action happening over there. So the new bridge adds another 50 feet, takes it over 200 feet. That's like a 20-story building to get up from the waterline to that new bridge.
And this new, taller Long Beach International Gateway helps the port scratch off one designation they didn't want.
Having the shortest bridge over a port in the United States. Well, that's gone now, and thankfully in a less tragic manner than what's happening on the East Coast.
In the aftermath of the Sunshine Skyway collapse, the federal government and the professional community, both from the engineering and maritime sides, invested a serious amount of time and investigation into the issue. One culmination was updated bridge codes that included requirements for consideration of vessel collisions. For highway bridges in the U.S., those specifications are put out by an organization called the American Association of State Highway and Transportation Officials, or AASHTO. But there are similar requirements worldwide, including in the Eurocode. A lot of infrastructure is designed for worst-case scenarios, but at a certain point, it just isn't feasible. It's something I've talked a lot about in previous videos. You have to draw a line somewhere that balances the benefits and the costs. If the code required us to design bridges with Armageddon meteorite or Godzilla protection, we just wouldn't build any bridges. It would be too expensive. And that's kind of true for ship collisions too. The mass and kinetic energy of the cargo vessels today is tough to even wrap your head around. We just couldn't afford to build bridges if they all had to be capable of withstanding a worst-case collision. Instead, for what engineers call high-consequence, low-probability events, codes often set the standard as some acceptable amount of risk. There's always going to be some possibility of an event like this, but how much risk are we as a society willing to bear for the benefit of having easy access across navigable waterways? In the US, that answer, at least according to AASHTO, for critical structures like the Key Bridge, is 0.01% probability in a given year. For some perspective, it's roughly the chance of rolling a Yahtzee, 5 of a kind, in a single throw. But it's an annual probability, so you have to roll the dice once every year. If you did it forever, it would average out to once every 10,000 years, but that doesn't mean it couldn't happen twice in a row. So, an engineer's job is to design the structure not to survive in a worst-case scenario, but to have a very low probability of collapsing from a vessel impact. And there's a lot that goes into figuring that out. This is the general formula for the annual probability of a bridge collapse due to ship collision. You have all these factors that get multiplied together. The first one is just the number of ships that pass under the bridge in a year. And there's a growth factor in there for how that number might change over time. Then there's what's called the probability of vessel aberrancy, basically the chance that one of those ships loses control. AASHTO has some baseline numbers for this based on long-term accident statistics in the US, and the designer can apply some correction factors based on site-specific issues like water currents and navigation aids. Then there's the geometric probability of a collision if a ship does lose control. When a vessel is aberrant, you don't know which way it's going to head. This gets a little complicated, but if you're familiar with normal distributions, it'll make perfect sense. You can plot a normal distribution curve centered on the transit path with one standard deviation equal to the length of the aberrant ship to give you an approximation of where it might end up. The area under that curve that intersects with the bridge piers is the probability that the ship will impact the bridge if it loses control. And this is really the first knob an engineer can turn to reduce the risk. Because the farther the piers are from the transit path, the lower the geometric probability of a collision. And this factor can be modified if ships have tethered tugs to assist with staying in the channel, something that wasn't required in Baltimore at the Key Bridge. But even if there is a collision, that doesn't necessarily mean the bridge will collapse, and this is where the structural engineering comes into play. The probability of a collapse depends both on the lateral strength of the pier and the impact force from the collision. But that force isn't as simple as putting a weight on a scale. It's time dependent, and it varies according to the size and type of vessel, its speed, the amount of ballast, the angle of the collision, and a lot more. Usually we boil that down to an equivalent static load. And based on some testing, this is the equation most engineers use. It's just based on the deadweight tonnage, basically how much the ship can carry, and its velocity. It's interesting that they settled on deadweight, which doesn't include the weight of the ship itself, but again, this analysis is pretty complicated, especially because you have to do it for every discrete grouping of vessel size and bridge component, so some simplifications make sense. And since this one assumes every ship is fully loaded, it's relatively conservative. Just for illustration, the ship that hit the Sunshine Skyway Bridge had a deadweight of 34,000 tons. The NTSB report doesn't estimate the speed at which it hit the bridge, but let's say around 5 knots. That would be the equivalent of a static force of around 56 meganewtons or 13 million pounds if the ship was fully loaded, which it wasn't, but there's no way to account for that in this equation. The Dolly has a deadweight of 117,000 tons and was traveling at roughly 5 knots on impact. That's equivalent to more than 100 meganewtons or 24 million pounds, again assuming the ship was fully loaded, which again it wasn't. But you can validate this with some back-of-the-envelope physics. Force is equal to mass times acceleration. We know the mass of the ship and its cargo from records, about 112,000 metric tons. To decelerate that mass from 5 knots to a standstill over the course of, let's say, 4 seconds requires roughly a force of 72 meganewtons or 16 million pounds. Even as a rough guess, that is a staggering number. It's 5 SpaceX Starships pointed at a single bridge pier. Designing a bridge to handle these forces is obviously complicated. It's not just the pier itself that has to survive, but every element of the bridge along the entire load path, including the foundation and, assuming the pier isn't perfectly rigid, the superstructure too. Again, it's not impossible to design, but it gets pricey fast, which is why designers have more knobs to turn to meet the code than just the strength of the bridge itself. One of those knobs is pier protection systems. Fenders can be installed to soften the blow of a ship impact, but for ships of this size, they would have to be enormous. Islands can be built around piers to force ships aground before they hit the bridge, but islands create environmental problems because of the fill placed on the river bottom. Plus, they get really big for deeper channels, so the bridge span has to be wider to keep the channel from being blocked. Islands can even affect currents in the water and the bridge structure, creating additional load on the foundation as they settle after construction. Another commonly used protection structure is called a dolphin. This is usually a circular construction of driven sheet piles filled with sand or concrete. Dolphins can slow a ship, stop it altogether, or redirect it away from critical bridge elements like piers. The new Sunshine Skyway Bridge used islands and dolphins to protect the rebuilt span, and actually, the key bridge had 4 dolphins, one on either side of each main support. Unfortunately, because it came at an angle, the dolly slipped past the protection when it lost control. It's important to point out that everything I've discussed is a modern look at how engineers consider vessel impacts to bridges. When the Francis Scott Key Bridge was finished in 1977, there were no requirements like this, and the bridge never had a major rehabilitation or repair that would have triggered adherence to the newer codes. Container ships the size of Dolly didn't even exist until around 2006, and we don't know what the ships of the future will look like. It's easy to say with hindsight that a bridge like this should have been better protected against errant ships, but if you say it for this one, you really have to say it for all the bridges that see similar maritime traffic. And that represents an enormous investment of resources for potentially not a lot of benefit to the public, given how rare these situations are. That's not me saying it shouldn't be done, it's just me saying that a decision like that is more complicated than it might seem. I don't expect we'll see bridge design code changes come out of this event, but vessel collisions will certainly be on the minds of the designers for the replacement in Baltimore. I'll let Rob explain.
When you take a look at photos of the Key Bridge, it looks like Maryland was doing a good job taking care of their bridge. So if the NTSB report comes back and says the bridge was in good shape, it's 100% the ship that's at fault, well, I don't think any of us are going to be really that shocked. But for the old Gerald Desmond Bridge here in Long Beach that used to be right here, well, the environmental impact report where they studied to build this new replacement bridge, the port staff really didn't seem too concerned about a maritime navigation failure. But a structural failure? Let's just say engineers score bridges out of 100 points. So you have a brand new bridge, it gets 100 points. On that scale, the old Gerald Desmond Bridge that was right here scored a 43. I mean, anything below 80 points, you get federal money to work on the bridge to try to rehab it and get it back into good shape. And anything under 50 points, it's so bad the federal government starts throwing money in trying to help you replace the bridge. That's how bad off the Gerald Desmond Bridge was. Salt from the air of the sea and decades of it sitting above seawater and all of that, just nice salt in the air eating away at the paint. Well, that paint was rated very poor on the old Gerald Desmond Bridge. And, you know, paint protects all the bridge members, all the metal from rusting out. And as Grady points out, every single member of a truss is really important if you want the bridge to stay in good shape and not fall down, right? Engineers also conducted a load analysis. They tested to see, as trucks drove over it, how the bridge was holding up. They found members of the arch main span were overstressed for all design trucks. So it didn't matter if you drove a big truck or a little truck. They were all causing problems with the bridge. And the concrete that those trucks drove on, it was all cracking up. It was rated critical. The port had to install big nets to catch big chunks of pavement that were falling off the bridge and could hit somebody on the head down here. So Long Beach had 4 objectives that this new bridge needed to meet in order to build it. And those goals may mirror some of the ones Baltimore may want to have when building their replacement bridge. Number 1, this bridge had to have a design life of 100 years, stay structurally sound for that long. 2, Long Beach wanted to reduce the approach grades on both sides, even getting up to 155 feet before. Sometimes you were driving up a 6% grade, and now that this thing's over 200 feet high, that would be way too steep. So they've instead built these huge freeway viaducts that go on and on for like a quarter of a mile to lift people in trucks gently up to that new bridge height. Baltimore's bridge already has some very long approaches to it, so I don't know whether they're going to replace the ramps approaching the bridge or not. It'll be interesting to see what they end up deciding to do. Number 3, provide sufficient roadway capacity to handle future car and truck traffic. The old bridge here was 2 lanes in each direction, 4 lanes. This widens it to 6. The Key Bridge in Baltimore was also only 4 lanes, but this bridge handles twice the traffic every day, compared to the Key Bridge back when it was open, right? And both the Key Bridge and the old Gerald Desmond Bridge had no shoulders for emergency vehicles and stalled cars to pull off to the side. And as you can see, the new bridge has these excellent shoulders on both the outside and the inside of travel lanes. So that makes the road a lot safer because you're not going to run into the back of a stalled truck in the dark. It's also a lot safer if you're not in your car because this bridge has a way you can cross it without being in a car. They've added this 12-foot wide pedestrian and bicycle pathway, which is about 12 feet wider than what they had before. Used to be on the old bridge, the only way across was inside a car.
It's a good start, certainly not perfect. Right now the path just hits this gate and stops.
The city of LA owns the next harbor bridge down that way. It's called the Vincent Thomas Bridge. It's also old, so it doesn't have a pedestrian walkway, so this pathway sort of just ends at the city limit because there's nowhere for it to go. But adding in a multi-use path like this one onto the new Key Bridge would be such a no-brainer. It could take a 4-mile bike ride from like Hawkins Point to Sparrows Point, down from 4 miles with the bridge path, from 22 miles right now without it.
And finally, the 4th goal, providing vertical clearance for new generation larger vessels, which the new bridge certainly has, and that must make the port very happy.
And I'm willing to bet that Baltimore will take that goal and maybe turn it on its side and talk about horizontal clearance and insist on a design that eliminates the risk of an elision like what happened on March 26 from ever happening again. Grady?
Thanks, Rob. If you love deep dives into transportation infrastructure, go check out his channel after this. But it's important to point out that this wasn't just a bridge failure, it was a bridge failure precipitated by a maritime navigation failure. Obviously, engineers who design bridges don't have a lot of say in the redundancy, safety standards, and navigation requirements of the vessels that pass underneath them. But if you look at the whole context of this tragedy and ask, how can our resources best be used to prevent something like this from happening again, reducing the probability of a ship this size losing control has to be included with the structural solutions like pier protection systems. I don't know a lot about that stuff, so I couldn't tell you what that might include, but I'm sure NTSB will have some recommendations when their report eventually comes out. Having tugs accompany large ships while they traverse lightly protected bridges seems like a prudent risk reduction measure, but that's just coming from a civil engineer. And speaking of risk reduction, I have to say that using risk analysis as a tool for design is really not that satisfying. We humans are notoriously bad at understanding probabilities and risks, and engineers are not that great at communicating what they mean to people who don't speak that language. That's how we get confusing terminology like the 100-year flood. And it's unsettling to come face to face with the idea that even if our bridges are designed and built to code, there's still a chance of something like this. Everything's a trade-off, but the people driving over the bridge or working on it had no direct say in where the line was drawn or whether it applied retroactively, even as ships got bigger and bigger. But I hope it's clear why we do it this way. The question isn't, can we design bridges to be safer? The answer to that is always yes. The real question is, how much risk can we tolerate? Or put in a different way, how much are we willing to spend on any incremental increase in safety? Because the answers to those questions are much more complex and nuanced. And if all bridges were required to survive worst-case collisions with ships like Dolly, we would just have a lot fewer bridges. But sometimes it takes an event like this to remind us that risks aren't just small numbers on a piece of paper. They represent real consequences, and my heart goes out to the families of the victims affected by this event. I hope we can honor them by learning from it and making improvements both to our infrastructure and maritime systems so that it doesn't happen again. The Key Bridge collapse is a really interesting case study because it combines two totally different areas of understanding. Obviously, I can approach it from the bridge engineering perspective, but there's just as much, if not more, to understand from the maritime side. Ships and marine navigation are literally a whole different world, and my friend Sam from Wendover Productions has an awesome video specifically about the crazy sophistication of the commercial fishing industry. I find it so fascinating to learn about the little details behind the industries I know nothing about, so honestly this entire series, The Logistics of X, is so good, and it's only available on Nebula. You probably know about Nebula even if you're not subscribed. It's a streaming service built by and for independent creators. No studio executives deciding what gets the green light, no advertisements, and no algorithm driving the content into a single style. It's just independent creators making stuff that they're excited about with as few barriers and distractions as possible between you and us. The website just got a huge update that completely redesigned the homepage, making it easier to find new stuff in addition to your favorites. My videos go live on Nebula before they come out here, and my practical construction series was specifically produced for Nebula viewers who want to see deeper dives into specific topics. I know there are a lot of streaming platforms out there right now and no one wants another monthly cost to keep track of, but I also know if you're watching a show like this to the end, there's a ton of other stuff on Nebula that you're gonna enjoy as well, so I've made it dead simple. Click the link below and you'll get 40% off an annual plan. Pay just one time $30 for an entire year's access at nebula.tv/practical engineering. Or if you have subscription fatigue but still want to support what I'm doing, you can get a lifetime membership. Pay once and you have access for as long as you and Nebula last. Hopefully that's a long time. If you're with me that independent creators are the future of great video, I hope you'll consider subscribing. Thank you for watching and let me know what you think.